Hi, so a biologist is researching a rare species of bacteria. At time equals t equals 0 hours, she puts 50 bacteria into what she has determined to be a favorable growth medium. 4 hours later, she measures 212 bacteria. So question A, assuming continuous exponential growth, what is the growth constant K for the bacteria? And question B, uses information to find the number of bacteria present after 12 hours. So first of all, because it's continuous exponential growth, right? Continuous exponential growth. We know that we're going to be using the formula A equals P times E to the KT, where P is the initial amount. E is it's this number 2.71 roughly, something like that. And then K would be the percent growth as a decimal, and T is the time, right? A would be the final amount. Excuse me. So let's put this together. What are we looking for? We're trying to solve for K. So what do we know? Well, we know that at time t equals 0 hours, she puts 50 bacteria into what she's determined to be a favorable growth medium. So this favorable growth medium tells us that they're going to be increasing in value, most likely. And time t equals 0 hours tells us that the initial amount is going to be 50 bacteria. So we can rewrite this formula as A equals 50 e to the kt. And now the question is, okay, what else do we have? Well, assuming continuous exponential growth, what is the growth constant K for the bacteria if she measures that 4 hours later, she has 212 bacteria? So when time equals 4 hours, when time is 4, she has 212 bacteria, or her final amount, A, is 212. So we can again rewrite this. We can write 212 is equal to 50 e to the 4k, we'll write this as. And this is just because t is 4, and we like to have our coefficients in front of our variables. So in this case, we have a variable k. We like 4 to be in front of it. Okay, so let's solve. We want to solve for k, so we divide both sides by 50. If you punch this into your calculator, 212 divided by 50 gives us 4.24. So let's kind of just scroll down a little bit. We have 4.24 is equal to e to the 4k. And now the problem is we need to get this k out of the exponent. How do we do that? Well, we have a tool for that called logarithms. We can take a log of base anything we want, log base 10, which is our standard logarithm, log base 15, 20, whatever we want. But since e and the natural log are inverses, it makes sense to take the natural log of both sides because that will cancel with the e. So we do that. We take ln of 4.24 equals ln of e to the 4k. We have this rule that allows us to bring the exponents out front of the logarithms when we take a logarithm. So this is equal to 4k ln of e. And now remember that ln of e is simply 1. So we can again just write this as 4k. In other words, we have that the natural log of 4.24 is equal to 4k. And now if we want to solve for k, we simply divide both sides by 4. This gives us that k is equal to, let's see, where's my natural log key? ln of 4.24 divided by 4, which is approximately, roughly, 0.36. So let's interpret this. This k value is the percent, or the growth rate, really. So as a percentage, this would be equivalent to about 36%, which means that per hour, right, because we're dealing with time, time equals, or the time is in hours. So per hour, the bacteria is growing by about 36%. So that's part A. So that's part A. We will label that. For part B, what is it asking us to do? Well, it's asking us to use this information to find the number of bacteria present after 12 hours. Okay, so now we're going to have our formula, A equals e to the kt, or P times e to the kt, sorry. We know that at time t equals 0 hours, she puts 50 bacteria in, so our normal starting value is going to be 50. And we multiply it by e and raise that to the kt. So what is k? K is 0.36 as we established. So this is 0.36. And then what is the time frame? Well, our time from question 2, or question B rather, is 12 hours. So we just substitute 12 into our time. And this is going to be equal to 50 times, where's e? Times e to the 0.36 times 12, which is about 3,759. And it ends in 0.43. Since we're dealing with bacteria, these are whole units of something, and so it makes sense to round up or down depending. Well, actually, it makes sense to only really round down, so we'll say that we have about 3,759 bacteria after 12 hours. Okay. Thank you so much for watching. Please follow me on Instagram and subscribe to my YouTube channel. Have a great rest of your day.